Can you see that? Okay, it's a bit dark, isn't it? Australian, I guess. Probably should use glove, I guess. Asbestos glove.
Now, if we put a lid on that didn't have these chairs in, it's extremely dangerous. Don't do it.
That's why I'm doing it with bare arms and no gloves.
One way, one the other way. So right now, they're boiling from a liquid to a gas. The nitrogen gas is going out of this safely. One way, one the other way. We're going to rapidly boil this in our cup of water.
Evaporating the liquid nitrogen by warming it, I guess. So, ideal gas flow, phase change, vapor pressures, and also rotational conservation of momentum, I guess, which is what we'll talk about today.
We count that as like a gas jet.
Sorry?
We almost count that like a gas jet of sorts.
It is a gas jet, yeah, sure. Yeah, it's just creating new volume by going from a liquid to a gas, and same as burning something in a jet engine, except that's a chemical process, right? Transformation to get larger volume than the liquid fuel.
Werden häufig zur Stromerzeugung bei Pumpspeicherkraftwerken eingesetzt. Hierzu ist der
German, if you understand German.
über eine Welle mit dem sogenannten Laufrad der Turbine.
So we talked last time about Pelton wheels for changing a stream of liquid into rotational momentum, but you can also do it with different turbine blades, not so different from the blades in the front of a jet engine, which have a different purpose, I guess, to pull air in and allow it to compress and go out the back. But this allows a stream to come in and then to be shot off to the sides, and by these angled blue blades, thereby give it rotational acceleration, I guess, a steady velocity of the thing. So I'm not sure which way it comes in this case. I guess they're not going to show it running. Abfluss is out, right? So yeah, so it comes in through here, gets fed into the turbine through these blades, turns it with these blades, and then it comes out through the center. So again, it's transferring its momentum into the system, and we've seen this before, but this is kind of what we'll talk about today, and that is that you could imagine each of these little cups being the vein that we had going across the floor horizontally, and that's how we'll try and treat it. It's the easiest way to treat it. But you see it's taking a velocity to the left-hand side. It's coming out of this hose at Vs, V static, and it's causing the vein to move at some velocity of the control surface and some incoming velocity into each of the cups, W, which we talked about. So that's kind of what we'll talk about today. I don't know what else we have. Oh yeah, this is kind of intriguing as well, I thought. The guy who had, was that me? So this is using water power to turn a wheel. Linear momentum of the water being transferred to these paddle blades, and the paddle blades then lifting through Archimedes' principle, filling up this open pipe, and then just twisting it to the center, and then horizontally to be able to move it on land. And so that's another use, I guess, for the kinds of things that we're talking about. Doing work, moving water up from the river level, elevating it so it can be flowed onto the bank and then be used for something. And I guess I don't know that we need to watch this. And of course, the other thing, you see them on campus, these sprinklers, but this is, I guess, a garden sprinkler where you can all figure out how it works. You get water coming through the central shaft into the blades on the top, or the pipes on the top. And depending on how it's angled, it will go around. You know that water coming out of this would turn it looking down from the top clockwise, just from the shape, the location of the jets coming out intuitively. And so that's the problem that we'll look at today, to be able to see what controls the velocity that head will go at, what happens if you hold the shaft static. And probably you could imagine that if you hold it static, that will be the maximum force you have to apply to get it to stay static, and the velocity coming out of it will travel the furthest. And if you allow it to rotate, the limiting rotation speed would be where the water is exactly coming out of the jet, and that bead of water would just drop to the floor immediately because of the velocity that the rotor is going at. Just a bit like what we talked about for the traveling vane. So there's some similarities on these. I guess he hasn't got it going yet. I guess, yeah. So you can all work out exactly where that's going. So that's what we'll talk about today. Questions? Any questions? I was going to just recap all our stuff on linear momentum, because that kind of feeds into rotational momentum. So I thought we would do that. Yeah. Yeah.
From the video, would it be that the velocity would be basically found through everywhere perpendicular to the face of the jet?
The velocity would come out in the direction that the pipe is pointing, and it would come out perpendicular to that area, and therefore if that was parallel to the direction of rotation, it would come out parallel. If it was at 90 degrees, it would go radially and have no rotational motion, right? You'd imagine that. We'll talk about that exactly today. So might be worthwhile. So this is what we'll talk about today. Conservation of radial momentum. And so I thought maybe what we might do is talk about this before we get going. So this is what we've talked about so far. And why not? Just do the whole thing. So Fire Department of New York. I know it's a kind of kindergarten example, but it's illustrative nonetheless. That we can take the velocities of the control surface and a static velocity, and we know that the static velocity is equal to the vector sum of the water coming out of the hose and the velocity of the ship, boat. The boat's not deforming, so everywhere around this boundary is the same control surface velocity. We know that we can write our conservation of momentum equation as sum of forces in some direction as equal to V static times the mass flow rate. That's it, sum of the mass flow rates. We know that we can always substitute this, which is where this is going to come from. So we know that we can always write this as the sum of the velocity coming out of into or out of the control surface plus the velocity of the control surface times the mass flow rate. The mass flow rate we would call W times the cross-sectional area times the density. Velocity area is meters cubed per second. So this term here is Q, uppercase Q. Together, all these three terms our mass flow rates. And I guess the other thing that we need to remember is that if we have our control volume, then the behavior we have is relative to that boundary, and we can define the two components, x and y, so that V1 here and V2 here for mass flow rate term, this is always positive outwards and negative inwards, and for the velocity or relative to the boundary velocity, this is always positive in the direction of the coordinate direction, and so we just need to follow this sign convention. And so the other thing that we did was that we simplified this, so this expression will always work. It simplifies if it's steady state, because if you remember, if we talk about the three examples we talked about, I'll just draw them in Cameo on the side here. We had this undershot weir, and we, bless you, yes indeed. I guess probably would draw it at the top of here. Actually, we can draw it like that. What did we solve? This was our flow rate in. We had pressures acting on this back, a force, which was this triangular distribution. I guess I don't want to relitigate these examples, but this is V2. And there's also a pressure acting on here, right? So, and we didn't use any values in our equations, we just did the equations. There's lots of examples in the notes or in the book in doing that. So you'll remember that we solved this by sum of forces in the x direction is equal to velocity times density times area times velocity for each of these. And we did that because we realized that it's steady state. And it's steady state because same amount is flowing in as flowing out. And if that's the case, then this term here, the product of these two terms, a constant times a mass flow rate, and we know that steady state mass flow rates sum to 0. Mass flow rate in equals mass flow rate out. That's what that statement is. And so a constant multiplied by that just changes this expression to this. It drops out this term because the velocity into the system is also equal to v, right? Because it's not moving. So steady state and static. We did the jetpack. Jetpack was exactly the same. Flow out of here, flow in here. We used exactly the same expression. We could have used fx, I think we called it w times density times area times w. That is because v, again, is equal to w in this case, and it's steady state. Okay. We did an example with the vane. So that's not static anymore. But again, it is steady state, right? Because you have a velocity coming in here, which was W1, and a velocity going out of here, W2. Steady state. But moving. And so it had some velocity of the control surface. It mattered that we gave a coordinate system to it, I guess. X and Y. And so I'll come back to it. So we said before, if it's steady state, we can get rid of this velocity term because it sums to 0. So again, we could solve it as sum of forces in the x direction. We only did it in the x direction, could do it in the y as well, was equal to W rho A W, exactly the same as this. This was velocity in the x directions for each of them. And this is a velocity in the y direction. The component of W2 in x is equal to 0. And so we and this was the sum of these terms, I guess, in this case. There was only one term, I think, right? Because this is orthogonal. There's only one term here because the other ones drop out. And I guess what I'm not sure I did mention is the one thing we know is we know the static velocity of the jet. We don't really know what W is. And so we can solve for W, but we have to write W as being equal to this. So W is equal to Vs minus Cs. And so if we do that, we know what this is. We substitute in here. So these covers for both of these. But now we can either choose this to be 0, in which case we'll get the maximum force out of this. So if VCS equals 0, then F equals F max. And if VCS equals the static velocity, then the force equals 0, but the velocity of the control surface equals max. So that was the problem we did then, right? And so all of these can be done with this, I guess I'm making the point, all of these can be done with this full expression, but this will always drop out. And so sometimes if you realize you don't need it, then you can just avoid using it. And the final one we did was the decapitated cylinder. Not bad. And for that, we had a velocity W1, a W2 I guess it was actually, and it would be in the x direction. And the sum of forces in the x direction are equal to the sum of W plus VCS. And this is the one case where we have to use this full term because it's non-steady state. That's because magically we're producing fluid in here, which is coming out here, and at some stage it's going to peter out because it's only a finite volume here. And so we have to use this. We could have used it in any of these other ones, but we chose not to because we realized that they were at steady state and this term just drops out. But you would have got the right answers using it in these other ones. And so the reason for this is that now if we look at the maximum force, and again we define this in terms of our coordinate system, x and y, z perhaps. This is the velocity of the control surface. If the velocity of the control surface is exactly, if we're not applying any force to this, to restrain it. If Fx is equal to 0, then this will only equal to 0 if W equals VCS. Equal and opposite to each other. Squirting out here pushes it in the other direction. Negative CS is just the opposite direction from this. Yes, Nicholas?
What is that? I noticed this for this one and the previous example. What does the little x mean in the exponent space for the W's?
This?
Yes.
In the x direction.
Ah.
Not an exponent in the x direction. Because we're just resolving in the x direction, right? We have one equation, we have three equations, but we're just choosing to resolve horizontally. Don't care what it's doing vertically, don't care what it's doing into the page. And so this will give the VCS max is when is equal to W, which we calculated from Bernoulli. If VCS is equal to 0, then Fx is maximum. So you see a pattern here. If you constrain it, you have the maximum force to resist it moving, because it makes sense, right? You're stopping it in its tracks. And if you allow it to move, then if you don't have a force acting on it, it will actually take the velocity, if it's weightless, of the stream that's coming out of it. Or the vane, the maximum velocity of the water hitting it relative to a static observer, which is what we calculated here, right? So that's kind of, it's probably worthwhile summarizing those things. So I guess the bottom line is you can always use this expression. It's always right. This is always written in terms of the relative to the boundary velocity. These two terms are always there, but in the steady state case, this term will just drop out because a constant, a non-deforming control volume translating all at the same speed multiplied by a sum of something that sums to 0 will be identically 0 as well. So that's what that is. So, and you could have used that here, you could have used it here, W plus VCS, and you'd got exactly the same results because VCS is 0. Okay? So, I don't know whether you're confused in this, but that's, hopefully that sets things out. We didn't do one example here. There's no particular component to this. Actually, you know, knowing that vane questions would be useful. We won't do anything as complicated as having an angle. But this is just the case in point to solve that expression. If you have a vane, and instead of us having a vertical surface here that it's reacting against, or here if it's reacting against, if it scoops up at some angle, then you can solve that just by taking the same conservation momentum equations we had before. The influent part is equal to W in density, W in times area. So this is W in, this is W out, I guess in these. So it's in the positive x direction, so it's positive. It's into the control volume, so it's negative, and it's multiplied by the air it comes into it. And when it goes out at a mass rate of flow, which is this. This is the cross-sectional area. This is the velocity as it goes out of the system. If the areas don't change, then it's the same velocity as it comes in, density. And now this is the velocity, to answer Nicholas's question. These are velocities in the x direction. We're resolving in x, so this is the component in the x direction, which is just going to be equal to this. Right? W1 is up here, W1 cosine 45 is here, sine 45 is this. And so that's just taking the angle we have. So I'm not going through this for any particular reason, but just to make the point that, one, we can have it coming out at angles, more complicated problem. And also we can resolve vertically. So we could sum forces in the z direction, in this case. And so this would be there would be a portion of this reaction going upwards. It'd be pushing down. You'd have the weight of the water that's pushing down. You'd have the weight of the trolley. And you'd have no component from this because it's orthogonal to this. And so this is the vector component going up, and the reaction on the ground pushing up. Bless you. This reaction here on the trolley, the force acting upwards. And the weight of the trolley acting downwards. So this is just summing in the other directions. So nothing with angles that you'll need to do with, except in your assignments, I guess. All right? I probably shouldn't have introduced that. I didn't really need to. But just wanted to make the point that, I guess it makes the point that you can resolve forces in the x direction, which is all we've really done so far. All these 4 examples are just doing it in one direction. But you could, if you wanted to, do it in the other directions. So let's do something a little similar to what we did before. So rotational. Momentum. So I won't do it. I'm going to do it something different. I'm going to draw a vein that we've had before. Except slightly different. I'm going to extend that vein into the page. I'm going to have watercolor. I'm not using very many colors today. I'm going to do, this is lowercase r. This is an angle of rotation and a rotational velocity in radians per second. And what else? And a velocity of the control surface. And maybe what I'll call F theta. Is that what I want? Yeah, okay. So this is our sprinkler. Made a bit easier. It is like a vein getting squirted in and going upwards, but just moved around. I'm going to draw a control surface, which I've always done in grey before, so I apologize for doing it in red. So this is the control surface. And I'm going to write our expression for conservation of momentum. This would be, which is equal to write it? Yeah, I'm going to write it at so this last term here is mass flow rate. Velocity out of it, density and area. This would be area 2, I guess. And I drew the control volume as this because I want to ignore this W1 here. I want to imagine that water's coming up in the middle of this. By definition, this will not be moving. It's going round and round, but a velocity of the control surface here is kind of equal to 0. But the control surface volume here is a big number, so we assume that we're just using this one. So ignore this W1, and we can perhaps come back and explain that later. So what we want to do is I could multiply both sides of this times the radius times the radius. And it turns out that if we took B is equal to mv, remember? We talked about Reynolds transport theorem. Therefore, extensive parameter, intensive parameter, B is just equal to uppercase B over m, which is equal to v. If we look at rotational momentum, then we just have to write this, multiply this by r and this by r. So if we substituted this term here into Reynolds transport theorem, I won't do it, then we'd get this term here, which is just multiplying the mass, the momentum term by r and the force term by r. That's all. Don't need to do that. And so what we get from this is that this is called a torque, like a torque wrench, tightening the nuts, bolts on the head of your engine in your car if you don't have an electric car. And this would be W plus velocity of the control surface times mass flow rate times R. So. And the utility of this in this equation that you see at the top also is, I guess, that we can do two things. We can say that the velocity in the rotational direction is equal to r times omega. So this is radians per second times the lever arm, times lever arm, times, this is the actual velocity of the head. And the other thing that we'd like to get out of it, I won't use W, but I'll use power, is equal to the torque multiplied by omega. So if we know what the torque is, then we can calculate how much power we get out of the system. If we hold it static, the torque will be a maximum, but the rotation will be zero, so no power. If we allow it to go without restraint, the torque will be zero, but the velocity, rotational velocity, will be maximum, so power is zero. So somewhere in between those, we'll get our maximum power out of the system. Yeah, and so that's it. And so this is now our new expression to be able to solve, to do a rotational problem. Okay. So all we've done, multiplied both sides by r, realize that this is a torque, and that we can define these terms, and we can use this to calculate the rotational power in changing a linear stream coming out here into a rotational velocity. Okay. I don't know, probably it's easier to, well, fine, perhaps do an example. So I'll do, maybe we'll do an example, yeah, fine. Sprinkler example. I'll do it here, then I'll go and look at the, so this, the example I'm going to do is in your notes, it's right. So we didn't talk about cross products, so the example we'll do is just one, which is this. This is the example we do. And so, but I'll perhaps lay it out in a simpler form so that we can go through it rationally. So we have V theta. If we have something coming out at some angle out here, we would have rotation in this direction, which is omega, torque also applied positive in that direction relative to a center. So we talked about right-hand coordinate system, x, y, and z. The coordinate system for rotational is z, and then the fingers are the direction of rotation. It doesn't really matter. It work out the same in every direction. You just have to choose a coordinate system of how to do it. I guess this would be the radius to the head. Yeah, that's it. And I guess the other thing that might be worthwhile drawing on this is that physically, if I draw a side profile of it, this is what it looks like. Perhaps I should have drawn it horizontally, right? This is just a section directly through here. I won't leave that. And so we've got water coming in, and we've got water spinning out somehow from these portions at different angles, right, at this angle. And so we can write our equation for the sum of the torque is equal to the sum of the radius times velocity plus control surface velocities times mass flow rate. So per nozzle, and this, the example that we have has 3 nozzles, so coming out like a trident, I guess not a trident, but each at 120 degrees, there's 3 nozzles. So if the nozzle, if the inflow rate is equal to Q, so this is Q in, and so each one of these will be Q over 3 because of 3 nozzles. So Q per nozzle would be equal to Q total, maybe, over 3. W nozzle would be equal to Q over 3 divided by area. And so this would be the amount coming out of one nozzle. Mass flow rate would be what? It would be equal to Q times density. Mass flow rate per nozzle would be equal to Q over 3 times density. And yeah. So T total would be equal to this expression here. Sum of radius times the velocity out of the system plus velocity of the control surface multiplied by mass flow rate. And so the mass flow rate would be this. The velocity out of the nozzle would be this. So this is, the velocity is the same out of every nozzle, so it's just this same amount. The mass coming out of the system is the same as this. You could do it by calculating this per nozzle and doing the mass flow rate out of each nozzle multiplied by the velocity. Or you could do it in the ensemble, I guess, being a fancy word. Use the total flow rate out of the system, which is this, multiplied by the velocity out of the nozzle. So this is just, if you wanted to do it per nozzle, I guess I could do that. T per nozzle equals, probably making this more complicated than it needs to be, W plus VCS times mass flow rate nozzle. This is total. And so if you did it for each nozzle, then T total would be equal to 3 times T nozzle. Anyway, so that's laying it out as straightforwardly as I can. So the idea that this comes in is that this is almost like an unsteady problem. This is almost the gas cylinder. This water is suddenly arriving in here and it comes from nowhere. It doesn't come across a control surface because the control surface it's coming across is here, and we're not accounting for that because we're not resolving in that direction. We're only doing it rotationally. But we need to have these components in there. We have the same sign convention for the velocity of theta. So positive theta would be in this direction, v theta is this direction, which is also the positive directions for the torque and also the positive direction for the rotational speed, which we can link to each other. And so this is one way to do it, where we'd use this sign convention. So let's go and skip through the example, one of the examples out of the book. Need to know about cross products. This is exactly the problem. So this is the sprinkler. You see it's got exactly the same things that we've talked about. We've done a control volume that goes around it. We have the water squirting out at some velocity. It could be tangential to this control volume or tangential to the arc that the nozzle goes in, or it could be at an angle relative to that, which we can deal with. The water comes in from the inside, so we don't have to worry about drawing a control volume where we have a velocity across here. We've eliminated that. And we've made sure that we write our expression in terms of the velocity of the control surface. In this example, they've done it in, well, this is the example here. So if we want to calculate the torque on the shaft, it's the mass flow rate out times the radius times the velocity. So this would have been what we called W. This would have been what we called Q, A, no, just Q rho. And this is what we would have called R. And this would be the velocity of this arc here, the component that's in the direction tangential to the rotation. So this is V, and this is just the vector component of that. I guess this would be perpendicular to it, right? And this would be V sine alpha, but we don't need that. And I guess in this case, this could also be written as W plus VCS. But in this case, we're holding it static, so VCS is equal to 0. And then they do the same things that we did. Mass flow rate in the whole system is equal to the flow rate up here divided by 3 nozzles, but the mass flow rate is the flow rate in times the density. The velocity out is the mass flow rate out divided by 3 nozzles divided by the area, which is what we did. Yeah.
2 questions. One, I thought from when we were calculating V out, it was A was multiplied as the numerator, unless I wrote it wrong.
I don't know if it was, then it's wrong. Second question?
Second question, just to be sure. So we're treating thing W as the out velocity, correct?
W is the velocity out of the control volume, always. And so it also happens to be the flow rate in, it has to be the flow rate in divided by the area of flow would be the volumetric flow rate. So these are the things we calculated for. It is in the denominator. And so if we substitute those in here, you get this expression, which gives you the shaft torque that you have to apply to hold it static, which is the maximum. If you want to be able to then release it and calculate how fast the thing will spin if it's released, then the torque needs to be 0. And this question goes through the case where you have these jets now at different angles. And so how do we get that? So we have from this is equal to, in our parlance, this would be mass flow rate times radius times W plus VCS. We need to convert this W into, I guess it's I guess it would be W cosine theta, right? Because it's the velocity relative to, that's tangential to the control volume. Just as if we go back to this, this is tangential to our control volume. It's kind of in the x direction. And so if we wrote this out, this is equal to our uppercase m dot. This is our r. This is our w cosine theta, to take care of the fact that the angle has to be the magnitude of the vector acting in the x direction or tangential to the volume. And then this is our VCS. And the reason there's a negative sign here is in this example, they've just defined the velocity for this as being in the opposite direction to our positive, right? In what we did before, we said that we'd align these in the same direction. So VCS, the positive coordinate direction in this case is this direction. So this is a positive force, this is a positive velocity of the control surface, this is a positive Cartesian velocity of the water out of the system, and so they've just chosen to choose the control volume moving in the opposite direction. So that's why there's a minus sign. And so once you have this expression, you can substitute, so this would be what we had as W cosine theta here. And this would be equal to U out is equal to what we've called minus VCS. Just a sign convention. And so I won't belabor the point, but so the ultimate goal then is to be able to now take this expression, and you can do two things with it. You can calculate what the maximum shaft torque would be for flows coming out not just at 0 angle, when this would be maximum, but also for these other angles here, just by substituting it. And you can also allow it to rotate where there's no torque that's applied, and you can find out what the velocities are when it comes out of here. And so that's what's done just using this. And it drops out of this. So the maximum shaft torque will be when it's static. So in other words, when this term is equal to 0. So if this is U out. Which equals to minus VCS. They've chosen to write it in terms of radians per second. So V theta is equal to R omega. Omega is in radians per second. V is in meters per second. And so multiplying radians per second by a radius gives you, radians has no dimensions, so this would give you meters per second also. That's just a conversion. So they've substituted that in there, the book. And if you work it out, then you can find out if the shaft is at theta equals 0 degrees. So 0 degrees is parallel to this, right? 90 degrees, this would be 90 degrees. And this is 0 degrees. So intuitively, you'd think that it'd be hardest to hold this if it's at 0 degrees. If it's at 90 degrees, there's going to be no force acting in the circular arc direction, and so there'd be no force that's required. And so this magnitude, if this is 0, because it's held static, should be the maximum, and it turns out to be 231 Newton meters. So this is a torque force times a lever arm. If you want to know what happens if it's 0, then this can only be 0 if these two terms are equal to each other. This term is equal to this term. And so you could write this, I guess you could rewrite this as omega is equal to q cosine theta over 3 times a, and you'd move the r out. So setting this term equal to 0, that's the only way that this can equal 0. And so you set that, and if you do that, that's what they've done here. You end up with a rotational velocity, which is in radians per second. If you do the same for theta degrees, you end up with a smaller torque that you need to apply, 200 versus 231. And the velocity, again, would be less. You'd expect it to be. Do it for 60, the torque is less, and the velocity is even less. They don't do it for, and you can guess what it would be if it was 90 degrees. If it's 90 degrees, then by definition, the torque is going to be 0, and the velocity is also going to be 0. It won't work, right? If it was 89, then it would be very small. And so that's it. So I guess I wanted to show really that rotational behavior is really just a continuation of what we've done. All we did is we took our former equation for force, we multiplied both sides by a lever arm, we called this force times the lever arm a torque, and we used this same relative behavior here. We merely noted that there's a sign convention that the velocity of the control surface and the outward velocity of the water and the forces are all in the same alignment. This is a positive direction. Of course, the mass flow rate out of this would be positive, right? Because the outward unit normal would look like this. So, bad. And I guess if you wanted to calculate the power, as we did last time, when it's held static, the power, since it's equal to the product of the torque and the rotational speed, held static, this is 0, power 0. Allowed to rotate at its own velocity, then the torque is 0 because you're letting it rotate, and this is a maximum, but still the power is 0. And so somewhere in between those two, when you attach an armature to it to generate electricity, then you get the maximum, you actually get power out of the system. And I guess you could imagine also that, when we talked about the vane, and you can rationalize this, is if you're feeding water in at some static velocity from a hose, the maximum velocity, if this has no force acting on it, if F is equal to 0, will be what? It has to be that this bead of water is just hitting the surface, and the surface is moving away from it. And so the actual velocity, maximum velocity of this vane has to be the static velocity that's coming into it. The corollary for this, if you did the calculation, would be that if you allow this thing to rotate at the velocity with no torque on it, then you'd find out that a bead of water that would come out at 0 velocity out of the system because it's moving in this direction as fast as the water's coming out. So the bead of the water would just drop to the ground. It'd be 0. So that would be the other component. Okay. All right. So have a look at those. I went through it carefully because there is a linear velocity problem on the test, a Vanish type problem. So moving but steady state. And there is a rotational momentum one as well. So it's encapsulated the rationale for this. And it's kind of the essence of what we're doing in this class anyway. So it covers it. Okay. Hate to bring that up, but that's perhaps helpful in choosing how to use your time. I know you all have busy lives, but enjoy homecoming, I guess, for today. Okay. Great. Thank you.